Hey everyone, today I want to talk about a very interesting paper, Neural ODE. It was the recipient of Best Paper Award at NeurIPS 2018. I'll start with the problem it tries to address, and to do so, I'm gonna switch over to geomatic and I'll choose a very simple example. I won't be talking about residuals or deep learning at all. I'll be demonstrating the key idea on a very simple equation in geomatic. So let me just get here and here on the screen you can see a trajectory of an ODE. The x-axis is the time and the y-axis is the y value. So you can see at time t equals 0, the initial condition y0 equals 1, so the trajectory starts off at 1, and at time equals 2, which is the end time, it ends at this point here. The first thing we'll do here is we'll modify a few inputs and parameters of this equation to see how this equation modifies, especially how this endpoint changes based on changes in different things like the initial condition or the parameter c or the start time t0. The reason to do so is because we want to understand two things. One, what can be modified in an ODE, and two, how it modifies the endpoint of a trajectory. Once we understand this, we will apply this to a problem where we want to get to a certain point, and then we'll learn how we can tweak these values to get to that point. We'll look at it later, but first of all, I'm going to change y0. So if I set y0 to something bigger, let's say 2, you can see the endpoint goes up. I can also animate y0 to, let's say, something very, very small, 0.1, and you can see how it changes. All right, let me also tweak the animation speed here because I think it's a bit higher, 0.001. Let me reset y0 to 1. The second thing I'll do is I'll modify the parameter c. Right now it's 0.5, and I want to animate it to something much bigger, like 1.5. And as you can see here, increasing c also reduces the endpoint. I'm going to reset it to 0.5, and lastly I want to modify the start time. Right now the start time is 0, and if I modify the start time t0 to something like -2, you can see it also lowers the endpoint. And I'm going to reset it back to 2, which is essentially not moving at all. So I should have reset it to 0. That was a mistake. Cool. So at this point, we still haven't gotten to the problem yet. We just have a pretty decent understanding of what a trajectory of an ODE looks like in 1D at least, and a couple of things that we can change in the ODE to modify the endpoint. Now let's talk about the problem. Let's say you're given a point P target here, and you want to follow the trajectory of an ODE to get to this point, but the input values or the parameters of the ODE have not been optimized yet, so you may end up at a point that's a bit different or far off from P target. And this is the key idea here. You want this point to be as close as possible to this point here. So essentially this point should be as close as possible to the target point here. Our parameter is the initial condition, which means that we want to modify the initial condition so that the endpoint can get as close as possible to the target point. The idea is to calculate the gradient of loss with respect to y0, and it's not very clear how we can do so. So here's an idea. What we'll do is we'll sample a lot of points along this trajectory and just try to understand how we can calculate the gradient of loss with respect to those points. So you can forget about the equation for the time being. And one thing I'll do is I'll just sample n to be the number of points, which is, let's say it's 10 right now. My times are, it's a linear space between 0 and 2 with n points. And what I do is I just do something like eval ODE, and my trajectory is called FWD0 and TS is my points. Cool. So you can see here I've sampled 10 points along this trajectory, and if you imagine that the path is discrete with these 10 points, and if I have the gradient with respect to the last point, which is P11, and if I want to calculate the gradient with respect to P10, just make sure you can see these points. So P11 is this point. Calculating the gradient with respect to P11 is pretty easy. And if I want to calculate the gradient with respect to P10, which is this point, what I can do is I can just use the chain rule. So I'll be using something like this thing where t is, in this case, is discrete. So this is time step t equals 10, I believe, and this is t equals 9, and I'll just be using chain rule to get the gradient with respect to P10. And what I can do now is I can increase the number of points to something bigger. For example, if it's 20, then I'm sampling points much closer in time. And if I keep doing this, for example, if my n becomes a much bigger number, in this case it's 30, and let's make it 40. In this case, what I'm doing is I'm taking very small steps in time, and I'm applying chain rule to calculate the gradient with respect to a previous time point, given gradient with respect to the current time point. For example, if I'm at P41, I can calculate the gradient with respect to time at P40 and so on. So I can just backpropagate using the standard backpropagation algorithm, given this discrete nature. So the next thing I can do is once these time steps are very, very small, I can just do some manipulation, and I can get a derivation of how this gradient changes over time, which is pretty accurate, and it has a very neat closed form solution, which looks like this. So here, A is the derivative of loss with respect to y at any given point in time t. This is how it's defined here. And what I'm doing here is I'm taking a very small step in time, t plus epsilon, which is basically what's happening here visually. And if I do so, then I can get this expression which gives me the gradient with respect to time step t given the gradient with respect to time step t plus epsilon. And with some manipulation, I can get this expression which describes the rate of change of the gradient in the form of an ODE, and this ODE runs backwards in time. So its starting point is t equals 2 in our case, and endpoint is t equals 0. That's the key idea. The cool thing about this is to calculate the gradient with respect to y0, we need to run one more ODE from t1 to t0, and we evaluate the endpoint of that trajectory, and that endpoint is nothing but the gradient with respect to y1. So let's see what that looks like. So here, let me remove these points first. I'm not sure if I can remove them. Let me render the whole thing all over again. So this is my annotation, and this is my forward trajectory. So what I'll do now is I calculate the gradient with respect to this point, the endpoint, and then I solve this backward adjoint ODE, which is nothing but this trajectory, and then I calculate what this endpoint here is. So this endpoint here is described by GPT0, and this is nothing but the gradient with respect to the initial condition. So once I have the gradient with respect to initial condition, all I have to do is take a gradient descent step, which is exactly what I do here. So just take note of this value here and the y position of this text box here. As soon as I click here, which performs a gradient descent step, the value changes like this. So this was one whole iteration of the key idea in neural ODE, which allows you to get the gradient of the initial condition without having to backpropagate through a differential equation solver. And let's run a few more iterations of this. So just to reiterate, we had the forward trajectory here, which the endpoint of which was a bit different from the target point. So based on that, we calculated the loss, and then we ran the backward trajectory of the gradient of that loss and evaluated the endpoint of that trajectory, which gives us the gradient with respect to the initial condition, and based on that we updated the initial condition using gradient descent. Let's do it all over again. So in the next iteration we start off at this point, and we get a new gradient, and we modify this point again, and let's do it a couple of more times. That's my second iteration, and this is my third iteration. And you can see here our endpoint is moving closer and closer to the target point by doing gradient descent. So this is the key idea which was presented in the neural ODE paper. It is how to calculate the gradient of some part of the ODE machinery, and in this case the only part that we tweaked was the initial condition. We can also modify things like the parameter C or the start time T. I'll cover the remaining two cases in a separate video.